All right, folks. In this video, we're going to work through procedures for calculating confidence intervals on different measures of effect size that we could pull from multiple regression. Now, when we're working with multiple regression, there are a number of different types of effect that we might be interested in based on what our specific questions are. Some of those we can get directly, other those we have to get indirectly. And so we're just going to work through procedures on how to go through and get confidence intervals on R-squareds, R-squared change, and then also partial, semi-partial correlations for individual predictors as well as F-squared statistics here. So before we get into procedures for calculating confidence intervals, want to make sure that we're clear on the different types of effects that we can pull out of multiple regression analyses and what those and how we would interpret those different effects. Okay, so if we start out with our basic effect size for our overall model, so our R-squared statistic for our full model. Okay, so this is just the R-squared statistic you would get in any simultaneous regression, telling us the proportion of total variability in our outcome that's attributable to the best linear combination of our full set of predictors. Okay, so if in this example, let's think about, because we'll start to divide this up, if we think about set A in this example as involving explanatory variables 1, 2, and 3, and then let's say we have a separate set that includes x4 and x5. So we've got 3 variables in set A, 2 variables in set B. If we're thinking about our R-squared for y given AB, our full set, this is just our R-squared for our full model. So if we regressed our outcome onto all 5 predictors, this would be our R-squared for that full model that we're looking at. And if we go down through and think about what this would look like in terms of our Venn diagram, we've done sort of worked with this a little bit before in a previous lecture. We would think about this, our R-squared value is representing regions L, M, and N, right? This is unique to set A, this is unique to set B, this is variability in our outcome that's shared across both sets. So we're looking at these 3 regions divided by all the variability in our outcome. So this is going to be L, M, N, and O here. Okay. So if this is our R-squared for our full model, given sets A and B, we can also think about calculating an R-squared for some reduced model. Okay. And in this case, let's say that this is just the R-squared for set A. What this is going to give us is it's the proportion of total variability in Y attributable to the best linear outcomes or best linear combination of predictors that are just in set A. Okay, and so again, if we're looking at this for R-squared of Y given A, we're just looking at, this is just a model where we just run predictors 1, 2, and 3 that are associated in set A. And so this is just going to be regions L and M, once again over the total variability in our outcome. L, M, N, and O, that's going into the denominator. That's all of the variability in Y. But for our reduced set, where we just have predictors 1, 2, and 3, we're just looking at L and M over the total here. Okay, so if R-squared given sets A and B, this is our full model. R-squared for Y, this is just looking at, or R-squared for Y given A, this is just our reduced model with just set A variables in there. Right. We can also go through and we can start looking at model R-squareds that are going to be sort of analogous to some of the single unit partial coefficients that we talked about. And what we can do is we can think about an analog semi-partial R-squared for a set of predictors, right? And within the context of hierarchical regression, we would often think about this as equivalent to an R-squared change statistic. So what we're looking at here with our squared semi-partial correlation for set B, right? This is going to be the R-squared, the proportion of total variability in Y that's just unique to set B. So we've got our R-squared for B, after accounting for stuff that's in set A. And so we can think about this again in terms of our hierarchical regression. If set B is what's being entered in the second step. This is going to be R squared change for set B. So if we're looking at this, right, we've got the unique contribution of set B relative to all of the variability in A. Again, with our hierarchical model, if set A is in the first step, this is going to be captured in R squared for step 1, and then our R squared change is just going to be N, right? My total R squared at step 2 is going to calculate all of these, but my R squared change is just going to capture region N here. This is what's being brought in, that's variability in our outcome that's unique to set B, above and beyond what we're getting in set A. And so from a diagram standpoint, we're talking about region N, again, over all the total variability in Y. So this is L, M, N, and O in my denominator, but now in my numerator, it's just what's unique to set B. Now, if set B only involves one predictor, right? If instead of set A involving x1, 2, and 3, set B involving x4 and 5, let's say set A included x1, 2, 3, and 4, and set B just had the one predictor in x5, then what we would see is that our R squared change, or our R squared for Y given BA, is going to be equal to the squared semi-partial correlation for just the single predictor in set B. And we've talked about interpretations of our squared semi-partial correlations. Again, it's just being the unique contribution of this one predictor relative to all the variability in my outcome. Okay, so I can think about my model squared semi-partial model R squared as being equal to my R squared for my full model, right? That's going to be R squared for my full model is going to get regions L, M, and N minus R squared for set A. That's going to take L and M out of the equation, and all we're left with is just N. And so what we're interested here is the proportion of variability, total variability in my outcome that's unique to set B, whether set B is a set of predictors or a single predictor. All right. We can also talk about a partial model R squared, okay? Partial model R squared is going to give us the proportion of residual variability in Y that's attributable to set B, okay? This is different than my squared semi-partial correlation or my R squared change. My partial R squared, model R squared, this is just going to give me the variability in Y that's attributable to B, but it's going to be the residual variability in Y. So for this, what we're looking at, remember with our partial correlations, or our squared partial correlation, it's giving me of the residual variability in Y after controlling for other factors, of what's left over, what's attributable to set B. Okay, so once again, our numerator here is just N, right? We're still working with this piece of B that's left over, but our denominator has changed here. Whereas with our R squared change, or our squared semi-partial correlation, we're looking at the total variability in Y. With our squared partial model R squared here, what we're looking at is after we section out section A, after we section out set A, what's left over is N and O, and of what's left over after we pull out set A, what of that residual variability is associated or attributable to set B. Okay. Now, once again, if set B only involves one predictor, then our partial model R squared is just equivalent to the squared partial correlation for just that one variable. But again, if we're thinking about calculating this proportionally, my squared partial model correlation here is going to be equal to, and again, the numerator is going to be the same as what we had up here with our R squared change, right? It's going to be R squared for the full model, regions L, M, and N, minus R squared for reduced set A, my reduced model A, which is pulling out L and M, and so we're just left with N here. But what's different is my denominator is going to change. Now, instead of looking as we were with the semi-partial total variability in Y, here we're just looking at residual variability in Y after we account for set A. So this is going to be 1 minus R squared for my A set. And so what's left here is just N and O. So what we have with our squared partial correlation for the model is going to be in the denominator just my variability that's remaining after I account for set A here. And the last metric that we can take a look at in terms of thinking of effect sizes is going to be an F-squared statistic. F-squared is our formal metric of effect size for multiple regression. If we're going to go through and we're going to run power analyses, we're probably going to have to provide an F-squared. F-squared has a direct relationship to my partial correlation. And what we're doing here is, as we were before with our R-squared change or our semi-partial correlation and our squared partial correlation here, numerator for F is just the same. We're looking at what's unique to B here, right? So we're starting out with R squared for our full model, LM and N, minus what's attributable to set A, that's L and M, and so we're just left with N here. But what we're looking at in the denominator is just the error. So what's the unexplained variability in Y? Here, different from our partial correlation, what we've got is 1 minus R squared for our full model, right? And so in this case, diagrammatically, we're looking at the proportion of what's unique to B. So we have region N over the top of region O here, okay? And this that's left over, this is just unexplained variability in my outcome, okay? So again, what we're looking at in our F-squared statistic is variability remaining after we account for sets A and B, so our full model here. But the important thing to recognize across all of these metrics is the numerator for our semi-partial, squared, partial, and F-squared is identical, okay? In each one of these, we're just looking at region N, right? We're just looking at the stuff that's uniquely attributable to B. What's happening is that our denominators are just including different proportions of variability. For our R-squared change or our semi-partial, it's total variability in Y. For our partial correlation or squared partial correlation, it's residual variability in Y after we account for everything else. And then in our F-squared statistic, it's just our unexplained variability in Y. It's just our error. So this is 1 minus everything that it's explained is left with O. Okay, now this has important implications in terms of calculating our effect sizes and also in terms of interpretation. So just wanting to be clear how each one of these relates to one another before we jump into actually calculating intervals. Some interpretive norms. Again, our R-squared change and our semi-partial correlations are nice. We're interpreting these as proportion of total variability in Y unique to a set of predictors or a predictor. But in terms of standard benchmarks for gauging magnitude, no clear or good benchmarks there. Our squared partial correlations or partial correlations and our F-squared metrics, we give up some in terms of interpretability, in terms of like conceptual sort of understanding what's this really means. But what we do is we have some recommended benchmarks for roughly gauging whether or not we're talking about small, medium, or large effects with our partial correlations or F-squareds. And so again, always want to be careful. These aren't hard and fast guidelines. What constitutes a small effect in one study may be very different if we're looking at a different set of variables or a different outcome or a different area, but generally these are often used as guidelines for small, medium, and large effects for F-squared, squared partial correlations, and our partial correlations here. Right. All right, so we were clear on different metrics of effect and how we might sort of go through and interpret those. But what we want to do now is we want to start calculating interval estimates around these, okay? And so what we're going to do is we're going to start out with our R-squared statistic. R-squared, we know and love, everybody knows and loves R-squared. It's a proportion of total variability in my outcome attributable to variables in my model. But similar to some of our means-based statistics we did last semester, so like calculating confidence intervals around D or around some of those mean-based metrics. If I'm going to calculate a confidence interval for R-squared, what I need is some estimate of the non-centrality parameter that's pulled from whatever the test is of the effect I'm interested in looking at. Okay, so remember that what we did to get confidence intervals for the non-centrality parameter is we used this handy-dandy Steiger calculator, the Steiger NDC tool here. And what we can do is recall that we can plug in our inference test, whether it's an F, a T, or a chi-square. In this case, what I can do is I can plug in an F test from my output. I can enter the corresponding degrees of freedom here, indicate the interval estimate that I would like to get, and then it'll go through, and what this will do is it will calculate a lower and upper limit for my non-centrality parameter. And once I have a lower and upper limit for my non-centrality parameter, what I can do is I can back translate the lower and upper limit of my non-centrality parameter into upper and lower limits for my R squared. Okay, and the formula to do this, pretty straightforward. My R squared for my upper and lower limits are going to be the corresponding non-centrality parameter limit divided by the non-centrality parameter limit plus U plus V plus 1, where U is the number of predictors in my model. V is my sample size minus U minus 1. Correspondingly, U is going to be the degrees of freedom in my numerator. V is going to be the degrees of freedom in my denominator for my test here. Okay, so once I go through from my output, get my test, put that in here, get my non-centrality parameters, then I can go through and get upper and lower limits for my confidence interval for my R squared effect. Also important to recognize that my model R squared holds a direct relation with my F squared statistic. Specifically, F squared is going to be equal to my R squared divided by 1 minus my R squared. Again, if R squared is the total variability in my outcome that's attributable to my model, if I take 1 minus my R squared, I'm just left with error. We know that's what we're getting at with our F. And so what we can then do is once I have an upper and lower limit for my R squared, I can back translate the upper and lower limit for my R squared to get upper and lower limits of my F, therefore giving me an interval estimate for my F squared statistic. So one quick note before we move forward, that these procedures outlined in Smithson are based on the assumption that we have conducted a fixed effects model, right? And remember in our previous lecture we had talked about this fixed effects assumption is a basic underlying assumption of all of our regression models, and it's an assumption that we always violate, right? Because we're not specifically selecting values of our predictors. Our predictors aren't fixed effects variables, they're random effects variables. Now, as long as certain other assumptions are met, we don't worry about that too much, but note that these procedures assume a fixed effects models, and so if we're using these procedures with a random effects model, which is basically almost all regressions that we'd ever run in psychological science, remember that these upper and lower limits of these procedures should be considered an approximation. So, an example. In these data, what I've done is I've gone through and I've calculated run a regression model where I'm looking at quality of life, and I'm regressing quality of life onto 4 symptom clusters of post-traumatic stress disorder. So I've got symptoms of hyperarousal, symptoms of avoidance, symptoms of numbing, and symptoms of re-experiencing. So these are my predictors. Quality of life is my outcome, and we pulled these data from accident survivors who have come in for difficulties. So what we're looking at is the extent to which individual PTSD clusters, hyperarousal, avoidance, numbing, and re-experiencing account for variability and self-reported quality of life. Right? So we see our R squared statistic here is 0.146. So the best linear combination of hyperarousal, avoidance, numbing, and re-experiencing is accounting for about 14.6% of the total variability and quality of life in these data. So I've got my point estimate. What I want to do is I want to get a confidence bound around this. Okay, and so I know that to get my confidence bound, what I need to do is I need to get a non-centrality parameter, and then take that non-centrality parameter divided by the non-centrality parameter plus U plus V plus 1. Here, U is the number of predictors, V is our sample size minus the number of predictors minus 1. So we can know what we need to plug in there. But in order to get my non-centrality parameter, remember I need to have a test statistic. And in this case, remember that my model F here, so this is my F test for my overall model, is the test of my R squared. This is the test of the null hypothesis that my R squared value is equal to 0 in the population. Okay, and what we have here, we have an F statistic of 11.84 with 4 and 278 degrees of freedom associated with a very small p-value, giving us fairly convincing evidence that against the null hypothesis that my R squared is in the population is 0. Alternatively, thinking about this as the best linear combination of hyperarousal, avoidance, numbing, and re-experiencing accounts for no variability in quality of life. We have strong evidence here to reject that null hypothesis based on my F test. But for this purpose, what I'm going to do is I'm going to use this F test and corresponding degrees of freedom to load this into my Steiger non-centrality parameter calculator here. So I have an F test, so I'm going to choose F. My F statistic is 11.84. Degrees of freedom 4 and 278. 4, 278 here. I'm looking at a 95% confidence interval. Compute that, which gives me a lower limit of 20.828. An upper limit for my non-centrality of 76.145. And what I can do now is I can use these parameters to go through and get a confidence bound around my R squared. Okay, so if I do this, if I plug this in, so my R squared for my lower bound is going to just be my non-centrality parameter lower bound, 20.828 divided by 20.828 plus 4 variables in the model, 278. Is number of people in my sample minus number of predictors minus 1. Plus 1 here gives me a lower limit of 0.069 on my R squared. And then I can do the same thing for my upper, using the upper limit of my non-centrality parameter, 76.145. So plug that in. I get an upper limit of my R squared of 0.212, which then gives me my point estimate, my confidence bound 1.146 with plausible estimates of population value ranging from 0.069 to 0.212. Okay, and if we wanted to put together some sort of applied interpretation of this, we could say the best linear combination of re-experiencing avoidance, hyperarousal, and numbing symptoms expected to account for between 6.9 to 21.2% of the total variability in quality of life in a population of community for survivors exposed to serious motor vehicle trauma. Remember that anytime we're working with an interval estimate, this is giving us data-supported upper and lower limits for the actual population parameter. Okay, so this gives us our procedures for grabbing an interval around our R squared statistic. Okay. If we wanted, and so this would be procedures that we would go through and use if we were going through and doing this in SPSS. In Stata, it's actually a little more straightforward because basically the program does it for you. So what we would do is, let's say we ran a regression model where we regressed quality of life on a re-experiencing, avoidance, numbing, and hyperarousal. We go through, have the output for that. I didn't include that output here, but after I estimate this model, if I then go through and I enter estat esize, what this is going to do is it's going to give me my model R squared in addition to partial correlations for each one of my predictors, as well as 95% confidence intervals. And so, easy peasy, I don't have to go through non-centrality transformations and things like that. If I'm running this in Stata, Stata will just give me my R squared estimate along with confidence bounds automatically with estat esize. So again, here, point estimate of 1.46, lower bound of 0.069, 212 is the upper bound. We go back to, go back here, see that's exactly what we got working through this by hand within SPSS. Okay, so benefit of that, estat esize will just give it to you automatically with if you're working with Stata. All right, so that covers our R squared statistic, but sometimes we might be working with a hierarchical model, and our question might be, what is the unique contribution of a set of predictors to above and beyond sort of a previous set, things that we've loaded in the model here? And what we're asking about here would be looking at an R-squared change value, right? So what is the unique contribution of this set of predictors above and beyond what we already have in the model? Essentially what we're asking for is a semi-partial model R-squared, just that's unique for this set of predictors, right? Now the difficult thing about calculating a confidence bound around R-squared change is that we can't do it directly. If we're going to calculate a confidence interval around R-squared change, what we need to do is we first need to get an interval estimate around our partial model R-squared. Remember that what this is looking at in our partial model R-squared, what I want is what's unique in sort of the unique contribution of set B relative to the whole total variability in my outcome. That's going to be my semi-partial or my R-squared change. But because I can't get a confidence interval around that directly, what I first need to do is get a confidence interval around my partial R-squared. And my partial R-squared is going to ask, be giving me an estimate of the residual variability in Y after we account for set A, how much of that is associated with set B. So here, again, we're looking for the partial model R-squared, region N over region N over O, or N plus O, pulling out set A out of the equation here, okay? So what I know is that my partial R-squared here is going to be equal to R-squared for my full model, regions LM and N, minus R-squared for regions A, over the top of 1 minus R-squared for set A, okay? And if we look at this, we can say that, yep, what we've got, if we take the full model minus my reduced model, if I take LM and N and subtract L and M, I'm left with region N here, divided by 1 minus R-squared for my A, okay? This is the total variability minus L and M. We're just left with N and O here in the denominator, which is going to give me my squared partial correlation for my model. Alternatively, if I look at this, if I am looking at R-squared for my full model minus R-squared for my reduced model, this is also just giving my squared semi-partial correlation, or my R-squared change, divided by 1 minus R-squared for my reduced model. Again, this numerator just reduces down to getting us what's unique to set B, independent of things that are going on in set A. Okay, so we can go through and understanding how we get our partial R-squared from our model, remembering that we can take that partial coefficient and calculate an F-squared from it. F-squared is pretty easy. This is just going to be my partial coefficient for my partial R-squared here, over the top of 1 minus R-squared for my partial coefficient here. Again, this is leaving me with just the residual variability in my denominator. So again, here's the transform to get from my partial R-squared to my F-squared with this. Yeah. So upper and lower bounds of my non-centrality parameter, I can use those to give me a test for my R-squared change through R-squared for my partial. And what I'm seeing here is that the upper and lower bounds of my partial R-squared are going to be equal to my non-centrality parameter, upper and lower bounds, plus U plus V plus 1. In this case, I need to get an extra element. W is going to be the number of predictors in set A. U is going to be the number of predictors in set B. And then V is going to be N, total sample size, minus U, minus W, minus 1. And so if we take that, plug that back into our model, this is going to give us upper and lower bounds for my partial R-squared, which then I can go through and take those upper and lower bounds for my partial R-squared and get it back to my semi-partial R-squared, or my R-squared change. Okay, and this is pretty straightforward. We take my partial R-squared is equal to, or my semi-partial R-squared is equal to my partial R-squared times 1 minus whatever variability was attributable to set A here. And so what I can then do is substitute, use this formula to take upper and lower bounds for my R-squared, my partial R-squared, to get interval estimates for my semi-partial. Okay, so head might be spinning at this point, but essentially what we're doing is we want to get a confidence interval around our R-squared change. But we can't do that directly. But what we can do is we can calculate a partial R-squared for our model. And what we can do is we can get a confidence bound around the upper and lower limit for my partial coefficient using my non-centrality parameters. And then once I have a confidence interval around my partial R-squared, I can use those upper and lower limits to then go back through and get the upper and lower limits for my semi-partial or my R-squared change, which is really what I wanted to do in the first place. Okay, so if I'm going to go through and do an example here, what I've got is I've got a model similar to what same set as we were using before, but this time outcome is still quality of life. But this time I've got I've run a hierarchical regression. In set A, I've got PTSD and avoidance in my first step, okay? And then my second step, I've got avoidance and re-experiencing my first step. In my second step, I have avoidance and re-experiencing, but then I'm adding numbing and hyperarousal to this, okay? So if we want to think about this, step 1 just includes predictors in set A. Step 2 includes predictors associated with step A and step B. And so what we can do is use the statistics that we've got here to make our calculations. So again, my model with just avoidance and re-experiencing, my R-squared is 0.082. So avoidance in this model is telling me that avoidance and re-experiencing account for about 8.2% of the total variability in quality of life. However, a model with avoidance, re-experiencing, numbing, and hyperarousal, that model accounts for about 14.6% of the total variability in my outcome, right? And so what I can do with my hierarchical model is going to give me an estimate of my R-squared change, which is just my full model minus reduced model, gives me 0.063. But then what's helpful is that this is going to give me a specific inference test for this R-squared change. And this model is going to tell me whether or not I have evidence that this R-squared change is likely some non-zero value in the population. And so what I see is I have an F test here of 10.27 with 2 and 278 degrees of freedom, a very small p-value here telling me that I have fairly convincing evidence that the contribution of adding numbing and hyperarousal, right? The unique contribution of numbing and hyperarousal is adding non-zero variability to the prediction of quality of life within this model above and beyond re-experiencing and avoidance, okay? And specifically, my point estimate here is about 6.3% of the total variability in my outcome that's added with including numbing and hyperarousal, okay? So what I want is a confidence interval around 0.063, but I can't have that. What I can do though is I can't get that directly. But what I can do is I can calculate a confidence interval around my partial R-squared. Now this output doesn't give me my partial R-squared, but I can calculate it based on information provided here. Now remember that my partial squared coefficient is going to be equal to total variability in my R-squared for my full model minus my R-squared for my reduced model over the top of 1 minus R-squared for my reduced model. So here I have my full model, my reduced model, okay? So I've got that information here, and so what I can do is I can plug that in, R-squared for my model with my full set of predictors, 0.146, minus R-squared for my reduced model, 0.082, divided by 1 minus R-squared for my reduced model, 0.082, gives me a partial squared R for my model of 0.070, okay? Now this is different than my R-squared change, right? Because my partial coefficient here is giving me the proportion of residual variability in quality of life after controlling for re-experiencing and avoidance that's shared with the combination of numbing and hyperarousal. So as we generally see that my partial coefficient is larger than my squared semi-partial correlation, because this is looking at total variability in quality of life that's unique to numbing and hyperarousal. This is telling me the proportion of residual variability that's attributable to these predictors. But what I can do now is I can take this and I can get an interval estimate around this. So what I need, remember, is I need to get my upper and lower limits. This should be limits, not lower. But what I can do is I can get upper and lower limits around my partial coefficient by getting upper and lower limits of my non-centrality parameter and plugging it into this formula. So here, remember that U and V, U is predictors in set V, V is N sample size minus U minus W, which is numbers of predictors in set A, minus 1. And what I need to do to get my upper and lower limits of my non-centrality parameter is I need to use this F statistic that's the specific test for my R-squared change. Remember that what I'm wanting to get is I'm testing upper and lower limits eventually for R-squared change. And so what I'm going to do is I'm going to use this F test, testing whether or not this increase in my model R-squared is different than 0, or I have evidence of a non-zero increase here, right? So what I'm going to do is I'm going to pull my F test specifically for my R-squared change. I'm going to drop this into my non-centrality calculator. Again, I've got 10.27 with 2 and 278 degrees of freedom. This is an F test, 95% confidence interval, giving me a lower bound for my non-centrality parameter of 5.659, upper limit 41.369. What I can do then is take those upper and lower limits. I can drop those using this equation. So here's my lower limit, here's my upper limit, and what I can do is I can take these estimates that I've derived from my upper and lower limit of my non-centrality parameter and calculate these into upper and lower limits for my squared partial correlation for the model. Okay, so this is saying that my data are suggesting that about 7% that the combination of numbing and hyperarousal are accounting for about 70% of the residual variability in quality of life after we remove stuff associated with avoidance and numbing. And data-supported estimates of the population value are going to range anywhere from 0.2 to 1.28. Right? Now, this is fine, but this wasn't actually what we wanted to get. What we want is a R-squared for our confidence intervals around our R-squared change. And this is R-squared confidence intervals around our partial R-squared statistic here. But once we've got upper and lower limits for our partial coefficient, what we can then do is we can go through and calculate, use these upper lower limits to back translate to get confidence bounds around R-squared change. So we know that our semi-partial R-squared is going to be equal to my partial R-squared multiplied by 1 minus variability attributable for my reduced model. So what I can do is take for my upper and lower bounds for my R-squared change. So for my lower, I'm going to take the lower bound for my partial R-squared. I'm going to take that times 1 minus my R-squared for my reduced model, which is 0.082. Run that out, I get a value of 0.018. Same thing, I can take the upper limit of my confidence bound for my partial, it's 0.128. Plug that in, multiply that by 1 minus the R-squared for my reduced model, again 0.082, gives me a value of 0.118. And if I go through, this will now give me upper and lower bounds for my R-squared change. So based on this procedure, my point estimate of my R-squared change with the inclusion of numbing and hyperarousal, again, this is the proportion of total variability in quality of life that's uniquely attributable to numbing and hyperarousal, is about 0.063. 0.063 with data-supported population estimates ranging from about 1.8% of the total variability, unique variability in quality of life, to about 11.8% of total variability in quality of life, uniquely attributed to the combination of numbing and hyperarousal. Okay. So again, to get our confidence bound around our R-squared change, we first have to get a confidence bound around our partial correlation, and then use these limits to back translate into upper and lower limits for our R-squared change. Now the last thing we could do, if we wanted confidence bounds for F-squared, again we can get that from what we did here and what we got for our partial correlation. Again, remember that F-squared is going to be equal to our squared partial correlation divided by 1 minus our partial correlation. So here, our partial correlation is 0.07. If I go 0.07 divided by 1 minus 0.07 gives me an F-squared statistic of 0.075. And then I can just do the same thing using the upper and lower limits of my non-centrality, or excuse me, my confidence bound for my partial, using those, plugging those in, getting a lower and upper bound for F-squared, which will give me a confidence bound of, or a point estimate of F-squared for 0.075 with a 95% confidence bound ranging from 0.02 to 0.147. Okay, and this would be just if we were working with power analyses and we wanted to get a range of plausible values for population-based effect, and we wanted to, say, power our analyses to what we need for an F of 0.02 or an F of 0.147, we could go through and do this. So moral of the story is we can get confidence bounds around our R-squared change or our F-squared, but what we first need to do is derive a confidence interval for that partial coefficient, and then we can go through and back translate there. Okay. So this is how we would go through and do this in SPSS. This time, procedures in Stata are going to be the same. Okay. If we want to run a nest reg, this is just our partial or our hierarchical model within regression. Again, regression, quality of life on re-experiencing avoidance in step 1, and then we're adding numbing and hyperarousal in step 2. This is going to give us our individual models, but down here, this is really what we're going to be looking at. This gives me my R-squared for set A, R-squared for set B. This is my model R-squared, or my R-squared change. This is my point estimate that I'm wanting to work with. But then here's my F-test and corresponding degrees of freedom for my R-squared change here. So again, once we've got that, all the procedures are the same. I'm going through calculating my partial coefficient just like we did before, going through calculating with my non-centrality parameter, lower and upper limits of my partial coefficient here, then going back through using these limits to back translate into upper and lower limits of my semi-partial or my R-squared change, and then if I wanted to, taking these estimates and getting upper and lower bounds for my F. Okay, so procedures in Stata, just like what we went through previously in SPSS, it's just sort of pulling the data stuff from down here. All right. Okay. Confidence intervals now. So these are going to be our bounds for our model test statistics. All right. What we want to do now is, though, we also maybe want to get confidence bounds for individual predictors, right? And so what we can do is we can start to generate confidence bounds around my squared partial correlation and my squared semi-partial correlation. And if we're thinking about set B as only containing one predictor, all the procedures that we just went through for calculating our R-squared R-squared change is going to give us intervals for both our squared partial correlation and our squared semi-partial correlation. So it's the same thing. We're just running a model where instead of set B having a set of predictors, we're just including just one predictor here. Okay. So again, my squared partial correlation is, my squared semi-partial correlation is just going to be my R squared for my full set minus the R squared for my reduced set, where my reduced set contains all the predictors except for my one variable of interest. Okay. Also, my squared partial correlation is going to be, again, R squared for my full set minus R squared for my reduced set, where my reduced set contains all of the variables except the one variable I'm interested, over 1 minus R squared for my reduced set. Alternatively, this numerator here is just my squared semi-partial correlation. Take my squared semi-partial correlation, divide by 1 minus R squared for my reduced set. That's what we've got going on there, and calculate my squared partial. Just like before, we can get upper and lower bounds for my squared partial correlation using my non-centrality parameter, given my test for my R squared change. Again, in this scenario, what we're doing is we're just having whatever predictor of interest, we're just including that in the final step of the model. And then what I've got is then can take the upper and lower limits of that and back translate that into my squared semi-partial correlation. So here I've got my semi-partial correlation is equal to my squared partial correlation times 1 minus r squared for my reduced set, and then going through and back translating that, entering those as we did before when we were talking about our model-based statistics. All right, so how to go through and do this in SPSS. Another example here. So what we've got in this set is we've got, again, working with the same data. Quality of life is our outcome, but in this situation, we've got hyperarousal, avoidance, and re-experiencing in set A, and then hyperarousal, avoidance, re-experiencing, and numbing in set the second step of the model. So set A contains 3 of our predictors, and what we're interested here is calculating a squared partial confidence bounds around the squared partial correlation and the squared semi-partial correlation, specifically for emotional numbing in this set. So the only new variable we're adding in step 2 of the model is just numbing. Okay. And so again, as before, we see the combination of hyperarousal, avoidance, and re-experiencing is accounting for about 9.2% of the total variability in quality of life. The full set of predictors, hyperarousal, avoidance, re-experiencing, and numbing, that's accounting for about 14.6% of the total variability, with numbing in and of itself accounting for an additional 5.4% of the total variability in our outcome that's unique to numbing here. So here's our R-squared change, but in this situation, R-squared change applies just to the inclusion of numbing, right? But we have our F, our degrees of freedom, and our test here. So we've set this up exactly as we did before. It's just that now in set B, it's just our one variable of interest. Okay. So what we need first, but we know that we can't calculate a confidence interval directly around our semi-partial correlation. But what we can do is we can calculate a confidence bound around my squared partial correlation. Now my squared partial correlation in this case is 0.06. And where I've got that, if I go down to this final model and I just take my partial correlation, so this is reflects the association of shared variability between numbing and the residual variability and quality of life after controlling for all my previous predictors is negative 0.244. If I square that, I get 0.06, which gives me my point estimate for my partial correlation here. Okay. Then what I do is I just run my non-centrality, get my upper and lower limits for my non-centrality parameter using my R-squared F test of my R-squared change specifically for numbing, because numbing was the only variable I had in that second step. And so it's F test of 17.584 with 1 in 278 degrees of freedom. If I plug that into my non-centrality parameter, I get upper and lower bounds of my non-centrality parameter of 4.836 and 38.197. So we've got that. And then, just as we did before, we can go through and use those non-centrality parameters using our equation here to get upper and lower limits for the squared partial correlation of numbing. Okay, so in these data, we would say about 6% of the residual variability in quality of life after accounting for re-experiencing, avoidance, and hyperarousal is associated with numbing, right? And plausible data-supported estimates for that squared partial correlation in the larger population, anything ranging from about 0.017 to 0.120 is going to be reasonable guesses based on the data that we've collected here. Okay. So what we've gone through, used the same procedures. We've got our confidence bounds around our squared partial correlation. And now what we can do is we can use our formula here to go through and get upper and lower bounds for our interval estimate for our semi-partial correlation. So if I do this, again, my squared semi-partial correlation is 0.054 for numbing. If I go down through, I can see if I take my squared part, or my semi-partial correlation, if I take 0.232 and I square that, I'm going to get 0.045. But we also see that we've already got that up here, right? Because this is my R-squared change for numbing, because numbing was the only additional variable added in that second step, and that my R-squared change is equal to the unique variability of the of the total variability in my outcome, what's unique to whatever was included, added in that extra step. Well, here only numbing is added to that extra step. So it's giving me, it's just my partial correlation just for, or my R-squared change for numbing. If I take 0.232, square that, I'm going to get that, right? So this is going to be our point estimate. If we go through using my equation here as we did before to take my upper and lower and upper limits for my squared partial correlation and use that to go through and get the lower and upper limits for my squared semi-partial correlation. Again, we've got my squared partial correlation times 1 minus R squared for my reduced model, which is going to be 0.092. Do the same thing. R lower bound of my partial correlation squared partial times 1 minus 0.092. My upper 0.120 times 1 minus 0.092. What this is going to do is it's going to give me confidence bounds for my lower and upper limit of my squared semi-partial correlation. So again, what this is saying is that within this model, about 5.4% of the total variability in quality of life is uniquely attributable to numbing scores, with upper and lower population estimates based on these data ranging from anywhere from about 1.5 to close to 11% of the total variability in outcome uniquely attributable to numbing once we account for hyperarousal, avoidance, and re-experiencing. Okay. And last, if we want to get an F squared specifically for numbing, we just use the same procedures as we did before. Again, we know that F and my partial correlation are hold a direct relationship. And so here what I can do is I can take my point estimate for my squared partial correlation and use that to calculate a point estimate for F squared. So 0.06 divided by 1 over 1 minus 0.06 gives me a point estimate of F squared of 0.064. Lower and upper limits, again, just taking upper and lower and upper limits for my squared partial correlation, translating those upper and lower limits for my F, resulting in point estimate of my F squared and corresponding confidence bounds here. Okay. So this is how we could go through and use the same sort of standard set of procedures that we use to calculate confidence bounds around our R-squared change statistic to go through and get confidence bounds for effect sizes for our individual predictors within SPSS. Okay. Now we can also do this in Stata, and it's a little bit easier in Stata because Stata gives us a little more output than what we were working with before in SPSS. So here we've run the same model, right? Here we've got we've regressed quality of life onto re-experiencing, avoidance, numbing, and hyperarousal. And then we request our E-stat E-size. And remember what E-stat E-size is giving us our model R squared with a confidence bounds. But then what E-stat E-size is also doing in Stata is it's giving me squared partial correlations for each one of my predictors, and then automatically creating confidence bounds for those. Now, these dots, these mean it's hit 0, so it's undefined. But what we're looking for here is we've got our R squared for our model and our confidence bounds. But here we also see that we've got our squared partial correlation for numbing, and Stata is calculating the confidence bound, lower and upper limit confidence bound for my squared partial correlation. So it's doing a lot of the work for us already, right? So with this, take some of the steps out of the way. So I know that my point estimate for my squared partial correlation for numbing is 0.059 with a confidence bound of 0.017 and 0.120. And once I've got that, now all I need to do is I know that for my squared semi-partial correlation, I just need to take the limits of upper and lower limits for my partial correlation and multiply that by 1 minus R squared for my reduced model. Now, I didn't run this in a hierarchical regression, and so I don't have that R squared for my reduced model given in this output, but I can get it pretty easy, right? Because I know that my R squared for my reduced model is going to be my R squared for my total model minus whatever was added with my squared semi-partial correlation. Okay, if my squared semi-partial correlation is the proportion of variability that's unique to numbing. Well, if I take my total my R squared from my total model and I subtract what was unique to numbing, then that's going to give me whatever the R squared would have been for a model that included re-experiencing avoidance and hyperarousal together. Okay, so if I go through and I do that, right, here's my R squared for my model, and here's what we can also ask for after we run our model, E-stat E-size, and then if I hit P-core and get my run the same model here, remember that this is going to give me my partial correlation, semi-partial correlation, squared partial, squared semi-partial. If I'm looking for my squared semi-partial here, I've got my R squared for my full model, and I can subtract my squared semi-partial correlation, and that's going to give me an R squared for my reduced model. And this is what my model R squared would be if I were just including re-experiencing avoidance and hyperarousal, is going to be 1.46 minus 0.054 is giving my reduced model is 0.092. Okay, it's the same thing we found in SPSS. We're just sort of getting this by subtraction. Okay, so now I've got my upper and lower bounds for my squared partial coefficient, and I've got R squared for my reduced model that includes just re-experiencing avoidance and hyperarousal. And so what I can do now is then calculate my upper and lower limits for my squared semi-partial correlation by taking lower bound for my partial multiplied by 1 minus R squared for my reduced set is 0.09. Same thing, upper limit for my partial, 0.120 times 1 minus reduced model there gives me my point estimate of my squared semi-partial correlation for numbing of 0.054 with a confidence bound going from negative 0.015 to 0.109. Okay, so again, in Stata, because it calculates the upper and lower bound for my partial correlation just right off the bat, a little bit of a shortcut saves me some steps, and so I can jump right into getting confidence bounds around my semi-partial. And then, just as we did before, I can use the upper and lower bounds of my squared partial correlation to get upper and lower bounds of F if I wanted to, if that's something that would be of interest to me, if I wanted to calculate an F squared specifically for numbing here. Okay? All right. So that does it. That works through procedures for calculating confidence bounds around R squared change, and then individual partial correlations, semi-partial correlations, and F squareds for individual statistics. Let me know if you have questions. There's big thing I would recommend with this, make sure that you have a clear understanding of what each one of these coefficients are and what they represent. If you do that on the front end, it'll make calculation and sort of the logic behind this much more straightforward. Okay, so again, good luck. Let me know if you have questions, and have fun.